Problem A. You were given a number with 5 or less digits. Determine if they're strictly decreasing.
Going down? That's what it means, right? Seems like you have to check them all, 2 at a time.
Problem B. Take a 100-point exam n times. The total of n-2 scores, excluding the highest and lowest, will be your final grade. You have already taken this exam n-1 times. For your final grade to be X or higher, at least how many points do you need in the last one?
I will try all the scores from 0 to 100.
It is possible to solve without trying them all, but it won't be easier. Problem C. Earlier, I asked, are the digits strictly decreasing? Among the positive integers for which the answer is yes. What is the value of the kate one from the smallest? From here on, you can't ignore the time limit.
This list ends with 98765433210, right? If you pick out part from there, you can list them all.
The key is that there are only about 2 to the power of 10 of them in total. And how to list them is up to you. Problem D. There are several main dishes and desserts. Choose one for each, and pay the total price. But if it exceeds a certain amount, you can pay that fixed amount instead. If you ordered all pairs once, how much would the total be?
You don't have time to order them all. But you can try all the main dishes. The matter is how many times you reach that fixed amount. If you line up the desserts in ascending order of price, binary search works.
You also need to sum up the ones below the fixed amount, but you can take the cumulative sums beforehand. Problem E. There is a nearly perfect binary tree. From a specified vertex, count the vertices with the specified distance. Do this a lot.
It's big, but it doubles each layer. So it won't be too deep. So if the distance is too much, you can say 0 and quit. Now, let's count the ones that are 4 away from 5. First, there is nothing if you go down 4.
If there were, they would be between 80 and 95.
If you go up 1 and down 3, there are 3. If you go up 2 and down 2, there are 2. You can't go up anymore, so that's it.
You just need to accurately do what we just did. Problem F. There is an empty box. Add and remove balls with numbers on them one by one. The balls can all be distinguished. After each operation, solve the following problem. How many ways are there to choose balls with a sum of k?
Putting balls in is easy.
It's what we call dynamic programming.
The problem is taking them out. Can I do the reverse calculation?
Yes, you can. Problem G. There are several electric parts. Each part has several red and blue terminals. There are as many red ones as blue ones. Prepare as many cables as terminals of each color, and connect a red one and a blue one with each cable. When choosing a possible way to do so uniformly at random, find the expected number of connected components.
First, instead of how many clusters, consider the probability of getting the cluster 1, 2, 3, 6, and so on, then add them all.
It's what we call the linearity of the expectation.
Let's start calculating this from the smaller clusters. And let's say we've gone up to 1, 2, 3, 6. If there are not as many red terminals as blue, it's no good.
They wouldn't be confined within themselves.
Even if there are, they could still connect to the outside. So for now, we want the probability of them not going out.
Just count the terminals beforehand, then you can find it.
But it might still split inside. And we want to subtract that probability.
What do you mean specifically by split?
Not all of 1, 2, 3 are connected to 6. For example, we don't want the cluster 3, 6. And we should already know that probability.
Again, 1, 2 might go outside. So multiply it by the probability of that not happening. That's all.
Thank you for watching.